Picture, for a moment, the absolute beginning, not a quiet, gentle dawn, but an eruption of such staggering violence that it defies all human comprehension. In a single, unimaginable instant, all of space, all of time, and all the energy that would ever become every star, every planet, and every one of us burst into existence. This was the Big Bang, the foundational event of our cosmos. For decades, this moment has been the ultimate frontier, a wall of energy so intense that light itself could not travel through it, leaving the universe's very first moments shrouded in complete mystery. We have been like detectives arriving at a crime scene billions of years after the fact, piecing together clues from the cosmic aftermath, but forever locked out of the room where it all began. What if, however, that room wasn't completely sealed? What if the cataclysmic violence of creation left behind a subtle, almost ghostly echo, a whisper from the very edge of time itself that we are only now learning how to hear? This is not just a philosophical question. It is the driving force behind one of the most thrilling quests in modern science. The concept we are exploring today is that of primordial gravitational waves, the universe's first space-time ripples. Think of the fabric of our cosmos as a vast, silent pond. The Big Bang was like a colossal stone dropped into its center. The initial splash is the hot, dense plasma of the early universe, but the stone also sends out ripples waves that travel outward through the very fabric of spacetime itself. These are gravitational waves, not made of matter or light, but of gravity itself, distortions in the geometry of reality. For the first fraction of a second after the Big Bang, theorists believe the universe underwent an explosive growth spurt known as inflation, expanding faster than the speed of light. It was during this incredible inflation event that the most powerful gravitational waves in all of history were generated, ripples born from the primordial energies that shaped everything we know. For a long time, detecting these first whispers seemed like an impossible dream, but science has a habit of turning dreams into reality. Today, we stand on the brink of a new era of discovery, where advanced observatories and brilliant minds are closing in on these ancient signals. The implications are staggering. Detecting these primordial ripples would be like finding a fossil from the first second of the universe, offering us direct evidence of what happened at the beginning of everything. And with this potential discovery comes a universe of theories, each more incredible than the last. In this video, we are going to embark on a journey to explore 30 of the most profound, mind-bending, and revolutionary theories about these first space-time ripples. We will delve into ideas that challenge our understanding of reality, from multiverses and cosmic strings to the very nature of what came before the Big Bang. This is a story of cosmic detective work, of humanity's relentless curiosity, reaching across 14 billion years to listen to the birth cries of the cosmos. So, get ready to peer into the deepest mysteries of existence, because what we are about to uncover will change the way you see the universe forever. So where do we even begin to look for these echoes from the beginning of time? Our first and most foundational theory provides the roadmap. This is the standard inflationary model, the cornerstone of modern cosmology. To grasp its power, we need to rewind the cosmic clock to a moment almost too brief to measure. We're talking about a tiny fraction of a second after the Big Bang, perhaps around 10 to the power of negative 36 seconds. At this point, the universe was a seething, incredibly dense, and hot soup of energy. But according to this theory, something remarkable happened. A strange form of energy, something like a field permeating all of space, took over. We call this the inflattened field, and this field had a peculiar property. It caused space itself to expand at a rate that is almost impossible to fathom, faster than the speed of light. This wasn't matter moving through space faster than light, which is impossible, but space itself stretching at an exponential rate. In less than a blink of an eye, a subatomic speck of this primordial universe was blown up to a size larger than our entire observable universe today. Now, here's where the magic happens for gravitational waves. Even in what we might think of as a perfect vacuum, at the quantum level, there is no true stillness. There is only constant, jittery activity. Tiny particles and energy fluctuations constantly pop in and out of existence. In that incredibly dense, rapidly expanding environment of the early universe, these quantum jitters in the inflated field itself were happening everywhere. As inflation stretched the universe to cosmic proportions, it didn't just stretch the space, it stretched these tiny quantum fluctuations along with it. Imagine drawing a tiny, wiggly line on the surface of a deflated balloon. Now, blow the balloon up to the size of a house. That tiny, jittery wiggle becomes a giant, landscape-altering wave. That's exactly what inflation did. Those microscopic quantum tremors were magnified into macroscopic ripples in the very curvature of space-time. These are the primordial gravitational waves we're searching for. The beauty of this theory is that it makes very specific, testable predictions. It tells us that this process should have created a background hum of gravitational waves, a stochastic signal, meaning it would come from all directions at once, like the static on an old television screen. But this static is a snapshot of the universe's birth. Furthermore, the model predicts a particular pattern or spectrum for these waves. Their strength should be directly tied to the energy scale at which inflation occurred. The more violent the inflationary expansion, the stronger the gravitational wave signal we should expect to find. This is why experiments like the BICEP array at the South Pole are so crucial. They aren't looking for the waves directly, like LIGO does for black hole mergers. Instead, they are studying the cosmic microwave background, the afterglow of the Big Bang. The reason, those primordial gravitational waves, as they traveled through the universe, would have left a unique fingerprint on this ancient light, a distinctive swirling pattern in its polarization known as B modes. Finding that pattern is like finding the signature of inflation itself on the first light of the cosmos, while a tentative detection announced in 2014 was later attributed to interstellar dust. The hunt continues with ever more sensitive instruments. The standard inflationary model remains our best guide, an elegant and powerful explanation that turns the quantum whispers of the infant universe into a cosmic shout we are desperately trying to hear. But right as the inflationary model solidified its place as the leading theory, a radically different idea emerged from the realm of string theory, challenging the very notion of a single, explosive beginning. This is Theory 2, the ekpyrotic universe. Forget a lone balloon inflating from nothing. Instead, picture our entire universe as just one three-dimensional surface, or a brain, floating within a higher dimensional expanse, often called the bulk. Now imagine another universe, another brain, floating parallel to ours in this hidden dimensionality. According to the ekpyrotic scenario, the Big Bang was not a singular creation event, but a dramatic collision between our brain and this neighboring one. Think of it as two gigantic, cosmic sheets smashing together in the higher dimensional void. This collision would have unleashed an immense amount of energy, heating our brain to an incredible temperature and filling it with the matter and radiation that would eventually form galaxies and stars. In this view, the Big Bang is a phase in an endless, cyclical drama of universes approaching, colliding, moving apart, and then approaching once again. This fundamental difference in origin story leads to a crucial distinction in the gravitational waves we might detect. In the inflationary model, the rapid stretching of space amplifies quantum fluctuations into large-scale ripples. But in the ekpyrotic model, the process is much smoother and slower. Instead of a violent, exponential expansion, the universe undergoes a period of gradual contraction before the collision. This contraction smooths out the universe, erasing any previous irregularities, making it exceptionally flat and uniform, which is one of the key problems inflation was designed to solve. However, this very smoothing effect has a direct consequence for gravitational waves. The quantum fluctuations that get stretched during this ekpyrotic phase are primarily those in the density of matter, not in the fabric of spacetime itself. The process is far less efficient at creating the kind of large amplitude, primordial gravitational waves that inflation produces. Therefore, a key prediction of this model is that the signal of these first ripples should be significantly weaker, perhaps even undetectable by our current technology. The spectrum of the waves, their distribution across different frequencies, would be a dead giveaway. Inflation typically predicts a nearly scale invariant spectrum, meaning the waves have roughly the same strength regardless of their wavelength. The ekpyrotic model, however, often predicts a spectrum that is tilted or blue, meaning the shorter wavelength, higher frequency ripples would be stronger relative to the long wavelength ones. Finding such a blue tilted spectrum would be a powerful piece of evidence, pointing away from a simple inflationary beginning and toward a more complex, multidimensional origin. This is where the connection to the multiverse becomes profound. If the ekpyrotic model is correct, it strongly suggests that our universe is just one member of a vast multiverse, a family of brains coexisting in a higher dimensional reality. The gravitational wave background becomes our first potential window into this hidden cosmic architecture. Most provocatively, this theory challenges the idea of an absolute beginning. If the universe is cyclic, then our Big Bang was not the start of time, but merely the latest rebirth in an infinite series. Each collision resets the cosmic clock, but the cycle itself may have no beginning and no end. Detecting the specific fingerprint of ekpyrotic gravitational waves would not just confirm an alternative to inflation, it would force us to completely rethink our place in the cosmos. We would have to grapple with the possibility that our entire history is just one chapter in an eternal saga of creation and destruction, playing out on a stage with dimensions beyond our perception. The search for these first ripples, therefore, is not just about understanding how our universe began, but about discovering whether it ever truly began at all. Yet another possibility pushes the boundaries of our imagination even further, suggesting that the Big Bang was not a beginning at all, but a turning point. This is the pre-Big Bang scenario, a concept arising from the deeper mathematics of string theory. If the ekpyrotic model presents a cyclic universe of colliding brains, this theory paints a picture of a single universe undergoing a majestic cosmic rebound. Imagine our cosmos not exploding from a point, but instead breathing. It inhales, collapsing inward from a vast, cold, and dilute state. All matter and energy draw closer and closer together, the temperature rising as space contracts. But instead of crushing down into an infinitely dense singularity, a point where our current laws of physics simply break down and give up, string theory provides a potential escape route. The theory proposes a fundamental limit to how small things can get, governed by the tiny, vibrating strings that are thought to be the most basic building blocks of reality. As the universe approaches this minimum size, a tremendous repulsive force stemming from the unique properties of these strings takes over, the contraction halts, and the universe bounces, beginning the expansion phase we find ourselves in today. In this view, the Big Bang is the moment of the bounce, the pivot between a long period of contraction and our current epoch of expansion. This dramatic transition from a contracting phase to an expanding one would have been an event of unimaginable energy, and like the inflationary model, it would have generated a storm of gravitational waves. However, the characteristics of these waves would be fundamentally different. During the long pre-Big Bang contraction, the universe was steadily getting smaller and denser. Quantum fluctuations in the gravitational field that existed during this era would have been amplified by the squeezing of space itself. Think of it like wringing out a wet towel. The act of compression forces the water out. Similarly, the contraction of the universe would have squeezed and amplified these tiny ripples, building up a significant background of gravitational waves before the bounce even occurred. The bounce itself would then imprint its own unique signature onto this existing sea of ripples. This leads to the most distinctive prediction of this model, a blue tilted gravitational wave spectrum. Unlike the nearly flat spectrum predicted by simple inflation, where ripples of all wavelengths have roughly the same strength, a blue tilted spectrum means the amplitude of the waves increases at higher frequencies. The shorter wavelength, higher pitched ripples would be noticeably stronger than the long wavelength, low pitched ones. This is a direct result of the pre-bang contraction. The shorter wavelength fluctuations are more effectively amplified during the squeezing phase, creating a spectrum that slopes upward toward higher energies. This provides a clear observational test to distinguish this theory from its rivals. If our future gravitational wave observatories detect a background hum that gets louder as they listen to higher frequencies, it would be a powerful clue that our universe has a history that extends far before what we call the Big Bang. The implications are staggering. A successful detection of this blue tilted spectrum would not merely confirm a different mechanism for the beginning of our expansion. It would shatter the concept of an absolute beginning. It would mean that time, as we understand it, extends backward into an era of contraction, a previous cosmic cycle with its own history, its own galaxies, perhaps even its own life. We would have to confront the possibility that our entire universe is part of an eternal sequence of bounces, a cosmic heartbeat with no start and no end. The search for these first ripples, therefore, transcends astronomy. It becomes a direct investigation into the nature of time itself, asking one of the most profound questions we can pose. Did our universe have a true birth, or was it simply reborn? Now, let's explore a theory that introduces a truly exotic structure into the early universe, not a field, not a bounce, but a crack in the very fabric of reality. This is the idea of cosmic strings. To understand them, we need to think about how the universe cooled. Picture the early cosmos as an immensely hot, unified sea of energy, where all the fundamental forces we know today, gravity, electromagnetism, and the nuclear forces, were merged into a single super force. As the universe expanded and cooled, it underwent a series of phase transitions, much like steam condensing into water or water freezing into ice. But when water freezes, the ice doesn't always form a perfect, uniform crystal. Sometimes, cracks and fissures appear, regions where the crystalline structure doesn't align perfectly. Cosmic strings are the cosmic equivalent of those cracks. They are hypothetical, one-dimensional defects, unimaginably thin, but containing an astonishing density of energy. Think of them as ultra-dense threads, thinner than a proton, but with a single inch of one possibly weighing more than a mountain range. These relics would have formed as the universe underwent its grand phase transitions, and once created, they would be virtually indestructible, stretching across the cosmos as it expanded. The connection to our gravitational wave story is direct and dramatic. These cosmic strings wouldn't just sit there passively. They would be dynamic, vibrating and oscillating at fantastic speeds, close to the speed of light. As they whip and oscillate through the cosmos, they can form kinks, loops, and even intersect with other strings. And every time a string moves, kinks, or interacts, it does something remarkable. It sends out ripples in space-time. Just as a whip crack creates a sound wave in the air, a cosmic string crack creates a gravitational wave in the fabric of the universe. Unlike the one-time burst from inflation or a bounce, cosmic strings would be a continuous source of gravitational waves. generating them throughout the entire history of the cosmos. This means they would contribute to the stochastic background we're searching for, but with a unique fingerprint. The signal would be a superposition of waves from countless string loops oscillating and decaying at different times and places across the universe, creating a persistent hum that has been present since the earliest epochs. Detecting a gravitational wave background with the specific signature of cosmic strings would be a discovery of monumental importance. It would be direct evidence for grand unified theories. The elegant frameworks that propose the forces of nature were once a single entity. The energy scale at which these strings form is far, far beyond what we can ever hope to reach with particle colliders like the Large Hadron Collider. So, finding them would be like using the entire universe as a particle accelerator, allowing us to peer into the laws of physics at energies trillions of times greater than anything we can create on Earth. It would tell us that the universe did indeed undergo these specific kinds of phase transitions, confirming a key prediction about how the fundamental forces separated and took on their distinct identities. Furthermore, the properties of the detected waves would reveal the characteristics of the strings themselves. The amplitude of the signal would tell us about the string's tension, how much energy is packed into each inch of it. The spectrum of the waves, their distribution across different frequencies, would reveal the network of strings, how many large loops versus small loops existed throughout history. Some models even suggest that if cosmic strings are real, they could have acted as gravitational seeds, the initial overdensities around which the very first galaxies eventually form. In this scenario, these cracks in space-time wouldn't just be leaving behind whispers. They might have played an active role in sculpting the entire large-scale structure of the universe we see today. The hunt for their tremors is therefore a hunt for the architects of our cosmic landscape. Now, let's shift our perspective from the grand architecture of cosmic strings to the fundamental physics of the early universe's cooling process. This brings us to our fifth theory, which focuses on cosmic phase transitions. To grasp this, think about what happens when you boil a kettle. The water starts as a liquid, but as you add heat, it undergoes a phase transition, turning into steam. Conversely, when you place water in a freezer, it transitions again, becoming solid ice. The early universe behaved in a remarkably similar way, but the transitions involved were far more profound, concerning the very laws of physics themselves. In the first moments after the Big Bang, the universe was so hot and energetic that the four fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were unified into a single superforce. As the cosmos expanded and cooled, it crossed critical temperature thresholds. At each threshold, a phase transition occurred, causing one of the forces to freeze out and separate from the others, much like ice crystals forming as water cools. The nature of these transitions is crucial. Some would have been smooth and continuous, like butter softening, but others could have been what physicists call first-order phase transitions. These are the dramatic, explosive ones. A perfect earthly analogy is the process of supercooling. You can sometimes cool liquid water below its normal freezing point without it turning to ice, if it's very pure and still. But the moment you disturb it, the transition happens catastrophically and almost instantly, freezing the entire volume in a flash. In the early universe, a first-order transition would have worked in a similar, spectacular fashion. It wouldn't have happened everywhere at once. Instead, tiny bubbles of the new, lower energy phase of the universe would have spontaneously nucleated in the seething, high-energy background, like the first ice crystals appearing in supercooled water. These bubbles would then have expanded at nearly the speed of light, their walls sweeping through the cosmos, converting the old, high-energy state into the new one. The collision of these expanding bubbles would have been events of unimaginable violence. When two such bubble walls met, the energy contained within them had to go somewhere. It couldn't just disappear. A significant portion of that colossal energy would have been converted into ripples in the fabric of space-time gravitational waves. The entire process would have been a chaotic, thunderous drumbeat of collisions happening across the universe, generating a deafening roar of gravitational radiation that would still be echoing through the cosmos today. The key insight here is that this mechanism provides a completely different source for a primordial gravitational wave background, one that is separate from both inflation and cosmic strings, yet potentially just as powerful. What makes this theory so compelling for scientists is its predictive power. The characteristics of the gravitational waves produced by such a phase transition are directly tied to the physics of the event. Most notably, the frequency of the waves is determined by the temperature of the universe at the time the transition occurred. Think of it like a bell. A large, massive bell rings with a deep, low-frequency tone, while a small, light bell chimes with a high-frequency ring. In the cosmic phase transition, the size of the bell is set by the Hubble radius at that moment, essentially the size of the observable universe at that specific temperature. A transition that happened when the universe was incredibly hot, and therefore very small and dense, would have produced gravitational waves with very high frequencies. A later transition at a lower temperature would have generated waves with lower frequencies. This gives astronomers a fantastic roadmap. By building observatories sensitive to different frequency ranges, we are effectively tuning our ears to listen for the chime of the universe as it froze into its current state, allowing us to pinpoint exactly when and how these monumental shifts in the fundamental forces took place. Detecting this specific signal would not just confirm the occurrence of a first-order phase transition, it would provide a direct measurement of the energy scale at which it happened, offering an unparalleled window into the unification of the forces of nature. Now we turn to a theory that reimagines the identity of one of the universe's greatest mysteries, dark matter. This is the concept of primordial black holes. We're accustomed to thinking of black holes as the end result of stellar life cycles, the dramatic corpses of massive stars that have collapsed under their own gravity. But what if the very first black holes in the cosmos predated the first stars entirely? This theory proposes that in the incredibly dense and turbulent environment just after the Big Bang, even before any stars had a chance to form, random quantum fluctuations could have been magnified to create pockets of space so overdense that they collapsed directly into black holes. Imagine a pot of water at a rolling boil, with bubbles of all sizes constantly forming and popping. In the seething plasma of the infant universe, some regions, by pure chance, would have had slightly more matter and energy than others. If one of these overdense regions was squeezed into a small enough volume, its own gravitational pull would have become so overwhelming that nothing, not even the radiation pressure from the intensely hot universe, could prevent it from collapsing. It would simply pinch off from the surrounding space-time, becoming a black hole born not from a star's death, but from the raw energy of creation itself. The formation of such an object would have been an event of singular violence, and it would have sent a powerful, unmistakable signal rippling outward. Unlike the relatively slow and spherical collapse of a massive star, the collapse of a primordial overdensity would have been incredibly rapid and likely quite lopsided. The distribution of matter in that initial pocket wouldn't have been perfectly smooth. This asymmetry is crucial. As the region collapsed, this irregular distribution of mass would have caused the fabric of space-time to wobble and shake violently. Think of a drop of water falling into a still pond. If the drop is perfectly spherical, it creates a neat, circular ripple. But if the drop is an odd, irregular shape, it creates a much more complex and churning set of waves. In the same way, The non-spherical, fast-paced collapse of a primordial black hole would have generated a powerful burst of gravitational waves, a sharp crack in space-time that would have propagated across the young cosmos. If this process happened not just once, but countless times throughout the early universe, the cumulative effect would be profound. The cosmos would have been filled with a stochastic background of gravitational waves, composed of the overlapping echoes from billions upon billions of these primordial formation events. Detecting this specific background hum would be a revolutionary discovery, but the implications reach even further, touching upon the nature of dark matter itself. For decades, the leading candidates for dark matter have been exotic, yet undiscovered subatomic particles, like WIMP or actions. However, primordial black holes offer a compelling alternative. If they formed in sufficient numbers, and if their masses fell within a certain range, they could account for all the unseen gravitational mass we attribute to dark matter. These ancient black holes would be invisible, scattered throughout galactic halos and intergalactic space, their collective gravity sculpting the rotation of galaxies and the bending of light, just as dark matter is observed to do. This creates a fascinating observational link. If a significant portion of dark matter is indeed made of primordial black holes, then the gravitational wave background they generated during their formation should have a distinct character. The spectrum of this background would directly reflect the mass distribution of those first black holes. Were they mostly small, perhaps with the mass of a large asteroid? Or were they monstrous, weighing as much as thousands of suns? The frequency of the gravitational waves they emitted is tied to their size. Smaller black holes would produce higher frequency ripples. By carefully measuring the properties of the primordial gravitational wave background, we could, in principle, weigh the dark matter. A confirmed detection would therefore achieve two monumental goals at once. It would reveal the origin of the first black holes and potentially solve the decades-old puzzle of dark matter, showing that it has been hiding in plain sight all along, not as unseen particles, but as ancient gravitational ghosts from the dawn of time. But what if the story of inflation is even more complex and varied than we've imagined? Our next group of theories suggests that the single inflattened field of the Standard Model might be just the simplest version of a much richer cosmic narrative. These are the alternative field theories, and they open up a universe of possibilities for the gravitational waves we might detect. First, let's consider the idea of K-inflation. In the standard picture, the inflattened field rolls slowly down its potential energy hill, driving the exponential expansion. But K-inflation introduces a fascinating twist. It proposes that the field's kinetic energy, the energy associated with its motion, behaves in a non-standard way. Think of it like this. In everyday physics, if you push an object, its speed increases in a predictable manner. But imagine a scenario where the relationship between the force you apply and the object's speed is strange. Maybe at high speeds, the object responds differently, as if moving through a peculiar kind of medium. In K-inflation, the physics of the inflattened field's motion is modified in just such a way. This modification has a direct and crucial consequence. It changes the speed at which disturbances travel through the field. We call this the sound speed. In the Standard Model, the sound speed of these perturbations is essentially the speed of light, but in K-inflation, this speed can be significantly slower. Why does this matter for gravitational waves? Because the quantum fluctuations that get stretched into density waves, the seeds of galaxies, travel at this sound speed. However, gravitational waves themselves, being ripples in spacetime, always travel at the speed of light. This creates a key difference. The amplitude of the primordial gravitational wave signal relative to the density wave signal is directly tied to this sound speed. A slower sound speed for the inflattened field's perturbations means that the gravitational waves end up being weaker relative to the density variations. So, if K inflation is correct, the telltale fingerprint of inflation imprinted on the cosmic microwave background, the B-mode polarization, would be fainter, more subtle, and harder to detect than the simplest models predict. Finding such a suppressed signal wouldn't be a failure. It would be a monumental success, pointing us toward a more intricate and exotic physics governing the universe's first moment. Now, let's add another layer of complexity with our eighth theory, multi-field inflation. Instead of a single hero, the inflated field guiding the universe's birth, picture an entire ensemble of fields working in concert. Imagine the early universe not as a simple, smooth hill, but as a vast, multidimensional landscape with valleys, ridges, and plateaus. As the universe evolves, it's not just one field rolling down. Multiple fields are evolving along this complex topography. This changes the story dramatically. A single field tends to produce a very smooth, featureless spectrum of fluctuations, a nearly perfect, uniform set of ripples. But when multiple fields are involved, their interactions can create much richer structures. The trajectory of the universe through this landscape can have turns, pauses, and transitions. For instance, one field might initially dominate the expansion, then transfer its energy to another field, which takes over. Each of these events, each turn in the cosmic path, leaves a distinct mark on the perturbations generated during inflation. Most importantly for our search, it can create sharp features or steps in the spectrum of gravitational waves. Instead of a smooth, featureless hum across all frequencies, the background could have distinctive peaks or dips at specific wavelengths. It would be like listening to a symphony versus hearing a single, steady note. The symphony has structure, with different instruments coming in at different times, creating a complex and beautiful pattern. A multi-field inflationary model would produce a gravitational wave background with its own unique melody, encoding the detailed shape of the inflationary landscape. Detecting such features would be like finding a detailed map of the fundamental forces at work during the universe's birth, revealing not just that inflation happened, but precisely how it happened, with all its twists and turns. These alternative theories remind us that the first whisper of the cosmos might not be a simple tone, but a complex chord, containing within it the secrets of a much grander and more elaborate origin story. But what if our foundational picture of a perfectly smooth and uniform beginning is itself an oversimplification? This brings us to a truly radical idea, the anisotropic universe hypothesis. For decades, cosmology has operated on the cosmological principle, the core assumption that the universe is both homogeneous and isotropic. Homogeneous means the matter is evenly distributed on the largest scales, like a well-mixed batter. Isotropic means it looks the same in every direction. There is no special axis or preferred direction in the cosmos. This principle is the bedrock upon which our models, including standard inflation, are built. It explains why the cosmic microwave background appears so incredibly uniform. But what if, in its very first moments, the universe was born with a slight but fundamental preference for one direction over others? Imagine not a perfectly round balloon inflating, but one that is slightly stretched, like a football, with a distinct long axis and a short axis. The anisotropic universe hypothesis proposes that such a primordial preference could have existed, leaving a unique and detectable scar on the gravitational wave background. Several mechanisms could have created this initial cosmic lopsidedness. One compelling candidate is the existence of powerful primordial magnetic fields. We know magnetic fields permeate galaxies and galaxy clusters today, but their origin is a major puzzle. Were they generated later by the motions of plasma within galaxies, or could they have been present from the very beginning? If these fields were primordial, woven into the fabric of space-time during its earliest phases, they would have represented a profound source of anisotropy. A magnetic field, by its very nature, defines a direction. It has field lines with a north and a south pole. In the seething plasma of the infant universe, such a field would have created a distinct pressure difference. Matter and energy would have found it easier to move along the field lines than across them. This directional pressure would have caused the universe to expand at slightly different rates along different axes. Expansion parallel to the magnetic field lines might have been faster or slower than expansion perpendicular to them, creating a universe that was ever so slightly elongated in one direction. Another source of anisotropic stress could be related to the fundamental fields that drove inflation itself. Perhaps the inflaton field was not a simple, solitary entity, but was accompanied by other fields that had a directional character, like a vector field that inherently points somewhere. The interaction between these fields could have imprinted a preferred direction on the very process of exponential expansion. The key point is that any such initial anisotropy wouldn't have just faded away without a trace. The violent processes that generate gravitational waves, whether from quantum fluctuations during inflation or from phase transitions, are exquisitely sensitive to the underlying geometry of spacetime. If that geometry was anisotropic, the gravitational waves produced would carry that signature. They would not be randomly oriented. Their polarization would show a statistical preference, a correlation that aligns with the universe's primordial axis. This would create a distinct, non-Gaussian pattern in the gravitational wave background. The term non-Gaussian is a technical one, but its meaning is profound for cosmologists. A Gaussian, or random, signal is like the static on an old television, completely chaotic, with no underlying patterns or correlations. The simplest models of inflation predict that the fluctuations, including gravitational waves, should be almost perfectly Gaussian. But an anisotropic source would break this perfect randomness. It would introduce specific correlations between waves coming from different directions. It would be like listening to the static and hearing, faintly, a recurring rhythm or a chord that repeats, telling you that the noise isn't entirely random after all. Detecting this non-Gaussian fingerprint would be a direct blow to the simplest interpretations of the cosmological principle. It would force us to rewrite the story of the Big Bang, acknowledging that our universe's birth was not a perfectly symmetric event, but a more complex, textured process with a built-in sense of direction. Finding such a pattern would not just add a detail to our models, it would fundamentally reshape our understanding of cosmic identity, suggesting that the universe itself has a hidden architecture, a subtle grain to its fabric that has been there since the very first instant. Even after the main event of inflation subsided, the drama of the early universe was far from over. The cosmos had been stretched to an incredible smoothness, but it was also desperately empty and cold in terms of the particles needed to build a universe. This leads us to the critical phase known as preheating. Think of the inflaton field not as a field of wheat, but as a vast field of energy, like a gigantic spring that has been stretched and loaded with potential. When inflation ended, this spring was released, but instead of a gentle, smooth unwinding, the decay of the inflaton field was a period of spectacular, chaotic resonance. The field began to oscillate wildly around the bottom of its energy hill, and through a process called parametric resonance, these oscillations became incredibly efficient at transferring energy. It's like pushing a child on a swing. If you push at just the right moment in the swing's arc, even a small push adds a lot of energy, making the child swing higher and higher. In the early universe, the oscillations of the inflaton field acted as that perfectly timed push, but on a cosmic scale. This resonant transfer of energy was so violent and efficient that it could rip the inflaton field itself apart, converting its colossal stored energy into a raging firestorm of fundamental particles the quarks, electrons, and other building blocks that would eventually form everything we see. But this process was anything but smooth. It happened in bursts and clumps, with some regions of space converting their energy faster than others. This created enormous inhomogeneities and sharp gradients in the density of the newborn plasma. And whenever you have massive amounts of energy moving in such a violent, non-linear fashion, you create ripples in spacetime. The rapid, large amplitude oscillations of the inflattened field during preheating would have acted like a colossal drum, beating out a powerful gravitational wave signal. This signal is distinct from the primordial waves generated during inflation itself. It's a secondary background, produced in the frantic moments when the universe was first populating itself with matter. The character of these waves would be a direct record of this turbulent birth, because preheating is a resonant and therefore somewhat stochastic process. The gravitational waves it produces would have a peaked spectrum, meaning they would be most powerful at a particular frequency range determined by the energy scale at the end of inflation. It would be a specific, dominant note in the cosmic hum. Detecting this note would give us a front row seat to the moment the universe switched on the lights, filling itself with the raw material for stars, planets, and life. It would reveal the detailed mechanics of how the inflattened field met its end, a dramatic finale to the inflationary epoch that set the stage for everything to come. Closely related to this is the possibility of early universe turbulence. Once preheating had filled the cosmos with a hot, dense plasma, this primordial soup would have been in a state of extreme agitation. We're talking about a fluid of fundamental particles moving at relativistic speeds, a maelstrom of incredible energy. In such an environment, it's almost inevitable that turbulence would have arisen. Turbulence is the chaotic, swirling motion of a fluid, something we see in water rapids or storm clouds. But in the early universe, this wasn't water or air. It was a plasma with energy densities beyond anything we can conceive, and its turbulent motions would have occurred at a significant fraction of the speed of light. This is magnetohydrodynamic turbulence on a cosmic scale. Just as the churning motions of ocean currents can generate waves on the sea's surface, the violent, turbulent motions of the primordial plasma would have generated gravitational waves. Enormous eddies and vortices, potentially spanning vast regions of space, would have acted as efficient generators for space-time ripples. The spectrum of gravitational waves from turbulence would have its own unique signature, different from both the inflationary signal and the preheating signal. Turbulence typically generates a spectrum where the wave amplitude decreases with increasing frequency, following a distinct power law. Finding evidence of such a spectrum would paint a vivid picture of the universe as a chaotic, swirling ocean in its infancy, a stark contrast to the smooth, controlled expansion of inflation. It would tell us that the moments following inflation were a time of incredible dynamism and violence, where the universe didn't just calmly transition, but seethed and churned as it settled into its new form. Together, the theories of preheating and turbulence remind us that the first second of cosmic history was packed with cataclysmic events, each capable of leaving its own resonant whisper in the fabric of space-time for us to discover. As we push our understanding of the universe closer and closer to the very first instant of time, we eventually reach a frontier where Einstein's beautiful picture of smooth, curved space-time may itself begin to fray. This brings us to two of the most speculative and profound ideas in our list, theories that use the gravitational wave background not just to study cosmology, but to test the very nature of gravity and reality at the most fundamental level. These are our quantum gravity probes. First, let's consider Theory 12, the possibility of a pixelated universe, as suggested by the framework of loop quantum gravity. Our everyday experience tells us that space is smooth and continuous. If you zoom in on a line, you can always imagine dividing it in half, and then in half again, seemingly forever. But what if that's an illusion? What if, at the tiniest possible scale, the universe has a fundamental graininess, a minimum size below which the concepts of here and there simply lose their meaning? This is a core prediction of loop quantum gravity, which proposes that space itself is not continuous, but is woven from tiny, finite loops, a fabric of discrete threads. The scale of this graininess is almost inconceivably small, at the Planck length, which is about 10 to the power of negative 35 meters. To put that in perspective, an atom is to a meter as a meter is to the size of the observable universe. The Planck length is 1,000,000 times smaller than that atom. Now, how could this fundamental pixelation affect something as vast as a gravitational wave? Gravitational waves are ripples in the fabric of space-time. If that fabric has a discrete, grainy structure at the smallest scales, it should affect how waves propagate, especially those with extremely long wavelengths. Think of it like watching a wave travel across a field of grass. From a distance, the wave looks perfectly smooth, but if you get down to the level of the individual blades of grass, you would see the wave's motion is slightly affected by the discrete nature of each blade. Similarly, a gravitational wave with a wavelength that is long enough to feel the granularity of space-time would be subtly altered as it journeys across the cosmos. This effect would be most pronounced for the lowest frequency gravitational waves, the ones that have been oscillating since the earliest times. Over billions of years of travel, these tiny, cumulative interactions with the granular structure of space could imprint a specific distortion on the wave. It wouldn't smooth out the ripple, but it might add a faint, high-frequency ringing or a slight dispersion, where different frequencies travel at marginally different speeds. Detecting such a signature in the primordial gravitational wave background would be direct, observational evidence that space is not a smooth continuum, but is indeed quantized. It would be one of the greatest discoveries in the history of physics, confirming that we have finally glimpsed the pixelated code underlying our reality. Our 13th theory takes us even deeper into the heart of gravity itself by asking a seemingly simple question about the particle that carries the gravitational force, the graviton. In the standard model of particle physics, every force is mediated by a fundamental particle. For electromagnetism, it's the photon. For gravity, according to quantum field theory, it should be the graviton. We've never detected one directly, but we assume it exists to make our theories consistent. Einstein's general relativity makes a very specific prediction about the graviton. It should be a massless particle with a spin of 2. Spin, in this quantum mechanical sense, isn't like a spinning top. It's a fundamental property that dictates how a particle behaves, especially how it interacts with space itself. A spin 2 particle is unique. It means that the gravitational wave it produces has a very specific pattern of stretching and squeezing space, a pattern we call tensor polarization. This is the classic plus and cross polarization that observatories like LIGO are designed to detect. But what if gravity is more complex? Alternative theories of gravity, proposed to solve puzzles like dark energy or to unite gravity with quantum mechanics, often predict the existence of additional gravitational waves with different polarizations. Some theories introduce a scalar component, a breathing mode that would cause space to expand and contract in all directions simultaneously. Others predict vector modes, a twisting polarization. If these extra polarization states exist, it would mean that the graviton is not a pure spin 2 particle, or that there are additional particles mediating gravity. The primordial gravitational wave background is the ultimate laboratory to test this, because it is a fossil from the earliest universe. It preserves the purest imprint of gravity's fundamental nature. By analyzing the polarization patterns within this background hum, looking for the telltale signs of not just tensor modes, but also scalar or vector modes, we could perform a definitive test of Einstein's theory on a cosmic scale. Finding a deviation would be a revolution on par with the discovery of general relativity itself. It would mean that gravity, the force that has shaped the entire cosmos, is not exactly as Einstein described it. The echo of the Big Bang would thus carry within it the secret identity of the graviton, revealing whether it is the lone spin 2 actor we believe it to be, or part of a more complex ensemble of forces that operated at the dawn of time. Now, let's turn our attention to one of the most intriguing hypothetical particles in physics, the action, and explore how its existence could have sculpted the gravitational wave background in 2 distinct and remarkable ways. First, consider the possibility that a vast cloud of these actions condensed in the early universe. To understand this, we need to know what an action is. It's a hypothetical particle originally proposed to solve a deep mystery in particle physics concerning the strong nuclear force, but it has since become a leading candidate for dark matter. Actions are theorized to be incredibly light, and crucially, they are what we call bosons. Bosons have a unique quantum property. They can all collapse into the same lowest energy state, forming what's known as a Bose-Einstein condensate. In the dense, cooling environment following the Big Bang, it's plausible that an immense number of actions did just that, creating a cosmic-scale condensate, a single, coherent quantum object spanning vast regions of space. This action condensate, however, would not have been perfectly stable. Like a spinning top that eventually begins to wobble, such a large quantum system could have undergone instabilities. Certain wave-like perturbations within the condensate could have grown exponentially, a process known as parametric resonance. As these instabilities developed, they would have caused the entire cloud to fragment into dense, swirling clumps or even to collapse in on itself. And here's the crucial part. These violent, large-scale motions within the action field involve the movement of enormous amounts of energy. Whenever mass or energy accelerates, it generates gravitational waves. The rapid fragmentation or collapse of an action Bose-Einstein condensate would have been a colossal event, sending powerful ripples through the fabric of space-time. The resulting gravitational wave signal would be unique, characterized by a narrow range of frequencies determined by the mass of the action particle itself. Detecting such a sharp, specific signal would therefore be a double discovery. It would confirm the existence of actions and reveal their role in shaping the early universe's dynamics, potentially even showing that dark matter itself was once a shimmering, unstable quantum sea that rang space-time like a bell. Our 15th theory takes the action in a different direction, placing it at the very heart of the inflationary epoch itself. This is the model of action inflation. In this scenario, the field responsible for driving the exponential expansion of the universe isn't a generic inflated field, but is specifically an action-like particle. What makes this so compelling is the unique nature of action potentials. Unlike the simple, smooth hills of standard inflation, the potential energy landscape for an action is periodic. It looks like a gently sloped, wiggly washboard. As the action field rolls down this slope, it doesn't glide smoothly. Instead, it undergoes tiny, rapid oscillations as it moves across each individual bump or wiggle in the washboard. These oscillations are the key. They represent a cyclic transfer of energy within the field, and this periodic motion leaves a direct, oscillatory imprint on the quantum fluctuations that are being stretched into cosmic structures and gravitational waves. The result is a gravitational wave spectrum with a remarkable feature. It wouldn't be a smooth, featureless curve. Instead, it would be decorated with a series of sharp, resonant peaks at specific frequencies. It would be the difference between hearing a steady hum and hearing a melody with distinct, repeating notes. These oscillatory features are a direct signature of the action's wiggly journey, and they encode precise information about the shape of its potential, the spacing and height of those washboard bumps. This is where the connection to string theory becomes profound. In string theory, action-like particles appear naturally, and their properties are tied to the geometry of the extra, compactified dimensions the theory requires. The specific pattern of peaks in the gravitational wave spectrum would therefore be a direct probe of this hidden geometric architecture. Finding such a pattern would be like discovering a cosmic radio station broadcasting from the extra dimensions of string theory, giving us our first experimental glimpse into a reality far beyond our familiar 3 dimensions of space. These action-related mechanisms show that the search for primordial gravitational waves is also a hunt for the particles that make up dark matter and a quest to unveil the complete geometric theory of everything. But perhaps the most mind-expanding implication of primordial gravitational waves is the possibility that they carry whispers from realities entirely separate from our own. This brings us to the profound concept of the multiverse, where these space-time ripples could become our first and only window into a cosmic landscape vaster than anything we've ever dreamed. Our 16th theory tackles a particularly dramatic multiverse scenario, the idea of a bubble collision. In many models of eternal inflation, our entire observable universe is just one bubble that nucleated in an eternally inflating background. Imagine a pot of water on a rolling boil, with steam bubbles constantly forming, expanding, and merging. In this cosmic foam, our universe is one such bubble. But what happens when 2 of these expanding bubbles meet? When their walls collide in the greater multiverse, the impact would be a cataclysmic event, releasing an astronomical amount of energy. This collision would send a spherical shockwave rippling through the interior of both bubbles. Inside our universe, this shockwave would manifest as a distinct imprint on the cosmic microwave background, and crucially, on the gravitational wave background. The signature would not be a random, isotropic hum. Instead, it would appear as a circular pattern of anisotropy, a kind of cosmic bruise on the sky. The gravitational waves generated by such a collision would have a specific directionality, arriving from a particular point in space and carrying a unique polarization pattern. Searching for such a telltale, circular signature is like looking for the scar of a long-healed wound, evidence that our universe once touched another in the fiery chaos of the multiverse. Finding it would be the first direct observational evidence that our cosmos is not alone, that we are part of a much grander, bubbling metacosmos. Building on this, our 17th theory proposes an even more subtle and fantastic possibility, that the stochastic gravitational wave background we measure might not be purely homegrown. Some of the faintest ripples permeating our space-time could be leakage from other universes entirely. In the brain-world scenarios we discussed earlier, where our universe is a 3-dimensional membrane floating in a higher dimensional bulk, gravitational waves have a unique property. Unlike all other forces and particles, which are constrained to move along our brain, gravity, being a property of space-time itself, can propagate through the bulk. This means that gravitational waves generated by colossal events in a neighboring universe brain could, in principle, travel through the higher dimensional space and subtly wash over our own cosmos. These alien waves would be incredibly faint, superimposed on the much stronger signal from our own universe's birth. But if we can someday tease apart the different components of the gravitational wave background, we might find a component that simply doesn't match any predictions from our own cosmic history. It might have a spectrum that suggests an inflationary energy scale different from ours, or a polarization that hints at different fundamental laws of physics in its universe of origin. Detecting such an exotic signal would transform cosmology. It would mean that by listening carefully to the vibrations of space, we are not just studying our own origin story, but tuning into a cosmic radio, picking up faint transmissions from entirely different realities with their own laws, their own histories, and perhaps even their own forms of life. The hunt for primordial gravitational waves thus becomes the ultimate act of cosmic exploration, a quest to listen not just to the birth cry of our universe, but to the murmurs of the multiverse. If the bubble collision and multiverse leakage ideas challenge the uniqueness of our universe, the next two theories challenge the very idea of a singular beginning. These alternative cosmologies propose frameworks so radical that they rewrite the entire cosmic origin story, and the gravitational wave background becomes the key piece of evidence that could confirm them. Our 18th theory is one of the most elegant and profound proposals in modern cosmology, Roger Penrose's conformal cyclic cosmology. This model does away with the concept of a definitive start altogether, suggesting instead that our universe is just one in an endless sequence of cosmic cycles, which Penrose calls eon. In this breathtaking vision, the distant future of our universe and the hot Big Bang of the next are one and the same event. Here's how it works. In our current eon, billions of years from now, the universe will have expanded to such an incredible degree that all matter will have decayed or been sucked into black holes, which will then slowly evaporate via Hawking radiation. What remains will be a universe devoid of any particles or distinguishing features, containing only massless radiation and gravitational waves. In this extremely simple, cold, and empty state, the universe effectively loses any sense of scale. Without massive particles to define a meter stick, the concepts of big and small become meaningless. Penrose uses a mathematical concept called conformal rescaling to argue that this vast, empty, cold end of our universe can be seamlessly identified with the hot, dense, small beginning of a new one. The infinite future is, mathematically, the next Big Bang, where do gravitational waves fit into this extraordinary cycle. Every eon would have its own violent history, filled with massive black hole mergers and other cataclysmic events that generate powerful gravitational waves. In the conformal cyclic cosmology, these waves, being massless, are among the few things that can pass through the transition from one eon to the next. As our eon expands and cools, these waves would stretch to become incredibly long wavelength ripples. When the new eon begins, these waves from the previous universe would imprint themselves onto the new one. Most strikingly, they would manifest as low-frequency, concentric circular patterns of temperature variation in the cosmic microwave background. Penrose and his collaborators believe they may have already found evidence of these Hawking points in the CMB data, which they interpret as the imprints of supermassive black hole collisions from a prior eon. Detecting a specific, low-frequency gravitational wave background that cannot be explained by events in our own universe's history would be the ultimate validation of this idea. It would mean that the static we hear in the fabric of space is not just the echo of our own birth, but a fossilized whisper from a cosmos that existed before time, as we know it, began. Our 19th theory takes a different approach to avoiding a singular beginning, exploring the idea of an emergent universe. What if the cosmos didn't explode from a point of infinite density, but instead emerged gently from a timeless, static state? In these scenarios, our universe begins not with a bang, but with a quantum fluctuation in a pre-existing, eternal meta-state. Think of it like a seed germinating. The universe could have existed for an infinite duration in a tiny, stable, static configuration, a cosmic seed. Then, due to a quantum transition, it suddenly shifted into a phase of rapid expansion, evolving into the universe we see today. This starting point avoids the thorny mathematical singularity of the Big Bang entirely, offering a much smoother launch. This different starting mechanism has a direct and testable consequence for gravitational waves. In the standard hot Big Bang model, the initial state is one of unimaginable heat and turbulence, perfect for generating a loud, stochastic background of primordial ripples. But an emergent universe begins from a state of quiet equilibrium. There is no initial violent explosion, no period of inflation driven by a mysterious inflated field. Without that incredible burst of energy to amplify quantum fluctuations, the generation of gravitational waves would be far less efficient. Therefore, a key prediction of many emergent universe models is a significantly weaker, or even entirely absent, primordial gravitational wave background. If we build increasingly sensitive detectors and consistently find nothing but profound silence where we expected a roar, it could be powerful evidence that our universe did not have a hot, violent beginning, but instead awoke peacefully from an eternal slumber. The absence of a signal would, in this case, speak volumes, pointing toward a cosmic origin story of serene emergence rather than cataclysmic birth. Together, these alternative cosmologies show that the hunt for the first ripples is about more than just confirming our standard story. It is a direct test of whether that story is correct at all. As we venture further into the cosmic unknown, we arrive at two of the most profound mysteries in all of science: dark matter and dark energy. Could the first ripples of space-time hold the key to understanding these enigmatic components that together make up 95% of our universe? Our 20th theory proposes a direct and dramatic link, suggesting that dark matter itself may have been a source of gravitational waves in the primordial cosmos. We often think of dark matter as completely inert, a ghostly substance that only interacts with the rest of the universe through gravity. But what if, in the extreme heat and density of the early universe, dark matter particles were far more sociable? Certain theoretical models, including some that propose a dark sector with its own forces and particles, suggest that dark matter could have interacted strongly with itself through forces beyond gravity. In this seething primordial plasma, these interactions could have been spectacularly violent. Imagine dense clouds of dark matter particles colliding and annihilating each other in bursts of pure energy, or perhaps unstable heavy dark matter particles decaying into lighter ones. Just as matter and antimatter annihilate to produce gamma rays, annihilations or decays within the dark sector would have released tremendous energy. And because these processes involve the rapid acceleration of immense amounts of mass energy, they would have inevitably generated ripples in space-time. This would create a gravitational wave signal with a spectrum directly tied to the mass and interaction strength of the dark matter particle. Detecting such a signature would be a monumental breakthrough. It would not only confirm the existence of dark matter as a particle, but also reveal its non-gravitational properties for the very first time, lifting the veil on the hidden physics of the dark sector that has governed the cosmos since its infancy. Turning from the dark matter that sculpts the cosmos to the dark energy that now dominates its expansion, our 21st theory asks an even more radical question: what if dark energy is not the constant, passive force we assume it to be? The standard model of cosmology treats dark energy as a cosmological constant, an unchanging energy density inherent to the vacuum of space that drives the accelerating expansion of the universe. But many physicists find this constant nature to be unsatisfying. Why should its value be fixed for all time? An intriguing alternative is that dark energy is dynamic, a field that evolves, much like the inflated field did during the universe's first moments. This concept, sometimes called quintessence, opens up a universe of possibilities. If dark energy is a dynamic field, it could have undergone phase transitions throughout cosmic history. Picture a late-time version of the early universe phase transitions we discussed earlier. As the universe expanded and cooled, the dark energy field might have suddenly shifted from a high energy state to a lower energy state, a process that would have occurred through the nucleation and collision of bubbles of new vacuum. Such an event, even if it happened billions of years after the Big Bang, would have been incredibly energetic, releasing a burst of gravitational waves that would still be washing over us today. This signal would be distinct from the primordial background. It would be a more recent chirp superimposed on the ancient hum, its frequency indicating the energy scale of the transition. Finding evidence for this would force a complete rewrite of our understanding of modern cosmology. It would mean that the accelerated expansion we observe today is not a fundamental constant of nature, but a phase the universe is currently going through, one that could potentially change again in the distant future. The echo of the first ripples might therefore carry within it the secret history of dark energy, revealing that the force shaping our cosmic destiny is anything but constant. But to truly test these grand ideas, we need to make a prediction, and if supersymmetry was a reality in the hot, dense conditions following the Big Bang, its disappearance would not have been a quiet affair. This is the core of Theory 22. At the incredible temperatures of the universe's first moments, supersymmetry would have been in its restored, unbroken state. Every known particle would have had a superpartner of equal mass, and the forces of nature would have been even more unified. But as the cosmos expanded and cooled, it crossed a critical temperature threshold. Supersymmetry had to break. In many compelling models, this breaking wouldn't have been a smooth, gradual process. Instead, it would have occurred through a first-order phase transition, the same kind of explosive bubble nucleation event we discussed earlier. Think of it as the universe undergoing a fundamental shift in its very operating system. Tiny bubbles of the new, broken symmetry vacuum would have spontaneously formed and then expanded at nearly light speed, colliding with each other and filling the cosmos. The energy released in the collisions of these bubble walls would have been staggering, and a significant fraction of it would have been converted into a thunderous burst of gravitational waves. The beauty of this prediction lies in its specificity. The gravitational wave signal produced by such a transition would have a spectrum, a distribution across different frequencies, that is directly tied to the energy scale at which supersymmetry breaks. This energy scale is precisely what particle physicists have been trying to pin down for decades. If supersymmetry exists at energies accessible to the Large Hadron Collider, the phase transition would have occurred at a correspondingly high temperature, producing gravitational waves in a frequency range that might be detectable by future space-based observatories like the Laser Interferometer Space Antenna, or LISA. A detection of this specific signal would be a monumental achievement. It would not only confirm one of the most sought-after extensions to the Standard Model, but would also tell us the energy at which it manifests, effectively doing the work of a particle collider far more powerful than anything we could ever build on Earth. The echo of supersymmetry breaking would be a direct message from the universe's first moments, revealing a hidden layer of symmetry that once governed all of reality. Theory 23 explores another dramatic consequence of supersymmetry, the formation of stable cosmic strings. We've already discussed cosmic strings as one-dimensional cracks in space-time, but their stability is a major issue in many models. Often, they are thought to be unstable, decaying quickly or connecting to other structures. However, supersymmetric theories provide a natural framework for creating cosmic strings that are truly stable, persistent threads that could survive from the early universe right up to the present day. The rich structure of supersymmetry, with its additional fields and topological possibilities, allows for defects that are protected by conservation laws, making them essentially permanent features of the cosmic landscape. If such a network of stable strings exists, it would be a continuous source of gravitational waves throughout cosmic history. As these infinitely thin, ultra-dense strings oscillate at relativistic speeds, intersect, and form loops, they would constantly lose energy by radiating ripples in space-time. This would produce a stochastic gravitational wave background with a very distinctive shape. Unlike the burst-like signal from a phase transition, the spectrum from cosmic strings is often described as nearly scale invariant, meaning it has significant power across a very wide range of frequencies. This makes it a potential target for multiple observatories simultaneously, from space-based detectors like LISA that are sensitive to low frequencies, to future ground-based detectors that could probe higher frequencies. Finding this specific background would be a double victory. It would provide strong, indirect evidence for supersymmetry by confirming one of its key cosmological predictions, and it would unveil the existence of these exotic, one-dimensional relics, giving us a direct probe of physics at energy's trillions of times beyond the reach of any conceivable particle accelerator. The hum of these ancient strings would be the sound of a symmetric universe slowly vibrating, a constant reminder of the perfect, balanced reality that existed at the dawn of time. But our exploration of the early universe's potential inhabitants doesn't stop with cosmic strings. The extreme densities present in the first moments may have allowed for objects even more bizarre than black holes to form, entities that challenge our very understanding of what matter can become. This brings us to the realm of exotic compact objects, starting with Theory 24, the possibility of gravastars and boson stars. Imagine a black hole, but one that has somehow avoided the dreaded singularity at its center. A gravastar, or gravitational vacuum star, is precisely such a hypothetical object. Instead of an infinitely dense point, its interior is theorized to be a bizarre region of dark energy, creating a kind of repulsive pressure that counteracts the crushing force of gravity and prevents total collapse. The surface of a gravastar wouldn't be an event horizon from which nothing can escape, but rather a thin, ultra-dense shell of matter, a crust teetering on the brink of becoming a black hole, but forever held in a state of precarious equilibrium. The formation of such an object in the primordial universe would have been a spectacular event. As an overdense region began to collapse under its own gravity, the internal pressures and densities would have reached such insane levels that a phase transition could have occurred, converting the core into this exotic dark energy state. This transition from collapsing matter to a stable gravastar would have been far less violent than the formation of a black hole. Instead of a catastrophic implosion into a singularity, it would have been more like a cosmic settling, a sudden crystallization into this new phase of matter. This gentler formation process would produce a gravitational wave signal with a distinct character. Unlike the sharp chirp of a black hole merger, the signal from a forming gravastar might be a quieter, more drawn-out hum, followed by a unique ringing as the object oscillates in its new stable state. These oscillation modes, the way the gravastar quivers after its birth, would depend entirely on its internal structure. Detecting this specific vibrational fingerprint would be direct proof that black holes are not the only possible endpoint for gravitational collapse, revealing a whole new class of ultra-dense objects lurking in the cosmos. A closely related exotic object is the boson star. While stars like our Sun are made of fermions, particles like protons and electrons that resist being in the same state, a boson star would be composed entirely of bosons. Bosons, such as photons or the hypothetical actions we discussed earlier, have the unique quantum property that they can all collapse into the same lowest energy state. This allows them to form a giant, coherent object held together by its own gravity, a single, gigantic quantum wave functioning as a star. A primordial boson star, forming from a cloud of light bosons in the early universe, would be incredibly dense and could mimic many properties of a black hole. However, its formation and dynamics would be governed by the wave-like nature of quantum mechanics. the collapse into a boson star would be a smoother, more wave-like process, and the resulting object could oscillate in complex, quantized ways. These oscillations would generate a continuous, monochromatic gravitational wave signal, a pure, persistent tone in the cosmic symphony, quite unlike the transient bursts from black hole collisions. Finding such a signal would not only confirm the existence of these exotic stars, but also provide stunning evidence of quantum mechanics operating on an astronomical scale. Theory 25 pushes the boundaries of speculation even further into the realm of one of science fiction's most beloved concepts, primordial wormholes. A wormhole is a theoretical tunnel, a shortcut through the fabric of space-time connecting two distant points or even different universes. The incredible energies of the Big Bang could have theoretically forged such structures spontaneously, weaving them into the very foundation of the cosmos. These wouldn't be the stable, traversable wormholes of fantasy. They would be microscopic, unstable entities, often referred to as quantum wormholes. Their life would have been fleeting. The moment one formed, the immense tension in space-time would likely cause it to pinch off and evaporate almost instantly. But in that brief existence, its rapid dynamics, the violent opening and closing of a gateway through space-time, would have been a potent source of gravitational waves. The signal would be a sharp, high-frequency burst, a cosmic pop as a wormhole blinked in and out of existence. Furthermore, if a network of these primordial wormholes managed to persist for even a short while, their interactions could have been incredibly energetic. Wormholes might have connected and disconnected, or oscillated, sending out complex ripples. Some theories even suggest that what we perceive as black holes could actually be the mouths of wormholes. If that were the case, then the mergers we observe with LIGO and Virgo might not be black holes colliding, but wormhole mouths connecting, an event that would produce a gravitational wave signal with subtle but potentially detectable differences from the standard black hole model. For instance, the final ring-down phase after the merger might have echoes, a repeated signature caused by gravitational waves bouncing around in the unusual throat of the wormhole before escaping. While firmly in the domain of speculation, the detection of any anomaly in gravitational wave signals that points toward wormhole physics would revolutionize our understanding of space-time, suggesting that the cosmos is not just filled with objects, but is itself perforated with tunnels and connections, a cosmic Swiss cheese with a hidden architecture written in gravity's earliest vibrations. Shifting our focus from the exotic objects that might have populated the early universe, we now turn to a different class of theories ones that reconsider the fundamental thermal and energetic history of the cosmos itself. These ideas explore how the universe's temperature and the behavior of its primordial soup could have left a unique mark on the gravitational wave background. The first of these, Theory 26, questions a key assumption of the standard timeline. What if there was an early, unexpected period where matter, not radiation, dominated the cosmos? In the standard cosmic story, the universe was initially so hot and dense that radiation photons and other relativistic particles, called the shots, their intense energy and pressure dictated the expansion rate. This radiation-dominated era is believed to have lasted for tens of thousands of years, right up until the universe had cooled enough for matter to take over. But some models suggest that even before the first nuclei formed in Big Bang nucleosynthesis, a brief era of matter domination could have occurred. This could happen if there were massive, unstable particles that decayed relatively slowly, their rest energy temporarily overwhelming the radiation and making the universe behave as if it were matter-dominated far earlier than expected. This subtle shift in the cosmic power balance has a profound effect on gravitational waves. Think of the early universe as a medium through which waves travel, like water of different depths. In a radiation-dominated universe, the water is stiff and responsive. Gravitational waves propagate through it with relative ease. But in a matter-dominated era, the water becomes deeper and more sluggish. The expansion rate of the universe changes, which directly affects how gravitational waves travel. More importantly, any gravitational waves that were generated during this early matter-dominated era would have a very different character. The processes that create waves, like phase transitions or the collapse of structures, would operate in a slower, more ponderous environment. This could lead to a gravitational wave background with a distinct bump or feature at the frequencies corresponding to that specific epoch. It's like finding a layer in a geological core sample that tells you the climate was unexpectedly cold for a short period. Detecting such a feature would force us to rewrite the very first pages of the universe's thermal diary, revealing a chapter where matter briefly seized control long before anyone thought possible. Our 27th theory digs even deeper into the properties of the primordial plasma itself by challenging the standard equation of state. This term simply describes the relationship between the pressure and energy density of a substance. For most of the early universe, we modeled the plasma as a relativistic gas with a very specific, well-understood equation of state. But what if the reality was more complex? The primordial soup was a seething mix of fundamental particles and forces, and it's possible that their interactions led to a non-standard equation of state. Perhaps unknown particles contributed extra pressure, or maybe the plasma had viscous properties, like a thick fluid that resists flowing smoothly. This change in the fundamental nature of the cosmic medium would have had a twofold impact on gravitational waves. First, it would alter how they are sourced. The efficiency with which any violent event, a phase transition, a turbulent eddy converts energy into gravitational waves depends on the stiffness and properties of the surrounding medium. A non-standard equation of state could make this process more or less efficient, either amplifying or suppressing the gravitational wave signal from a given event. Second, and just as crucially, it would change how the waves are damped. As gravitational waves travel through a plasma, they can lose energy by interacting with it. A more viscous or unusual plasma would dampen certain frequencies of gravitational waves more effectively than others, effectively acting like a cosmic filter. The stochastic background we might detect today would therefore not be a perfect record of the original waves. It would be a filtered version, its spectrum shaped by its journey through this exotic primordial fluid. Finding the signature of this filtering would be like an audio engineer analyzing a recording and being able to deduce the exact acoustic properties of the room it was made in. It would give us an unprecedented understanding of the true nature of the universe's first moments, not as a simple ideal gas, but as a complex, dynamic substance whose unique physics is permanently imprinted on the oldest vibrations in space-time. Now we arrive at the very edge of theoretical physics, where our understanding of space, time, and information itself is pushed to its absolute limit. These next two theories are among the most profound on our list, suggesting that primordial gravitational waves might be more than just echoes. They could be cosmic hard drives and holographic projections containing the deepest secrets of reality. Let's start with Theory 28, a concept that takes us straight to the infamous black hole information paradox. This puzzle, which has troubled physicists for decades, asks a simple but devastating question: what happens to information when something falls into a black hole? According to quantum mechanics, information, the specific configuration of every particle, can never be truly destroyed. But according to general relativity, anything that crosses a black hole's event horizon is lost forever, its information seemingly erased from our universe when the black hole eventually evaporates via Hawking radiation. This is a fundamental contradiction at the heart of physics. Now, how could this possibly relate to the Big Bang? Remarkably, our universe's beginning shares a key similarity with a black hole's end, a singularity. The Big Bang is a point of infinite density where our known laws of physics break down. This has led some theorists, like Roger Penrose, to propose a wild idea called conformal cyclic cosmology, which we touched on earlier. In this model, the information from a previous cosmic eon is not lost at the Big Bang singularity. Instead, it is encoded in the gravitational waves generated by the collisions of supermassive black holes from that prior universe. These waves, being massless, travel unscathed through the conformal rescaling that transforms the infinite future of one eon into the Big Bang of the next. In this breathtaking vision, the stochastic gravitational wave background we are trying to detect is not just a relic of our own universe's birth. It is a fossilized library, carrying the quantum information from an era that existed before time as we know it began. Detecting specific patterns or correlations within this background could be the first evidence that information is indeed preserved across cosmic cycles, solving the information paradox by showing that the universe itself has a form of cosmic memory etched into the vibrations of spacetime. This leads us directly to Theory 29, which is perhaps the most radical reimagining of reality on our list, the holographic principle. This idea, born from the study of black holes and string theory, proposes that our three-dimensional universe, with all its rich content of galaxies, stars, and people, is actually a projection of information stored on a two-dimensional boundary that surrounds us. Think of it like an incredibly complex and high-resolution hologram. On a credit card hologram, a two-dimensional surface creates the illusion of a three-dimensional image. The holographic principle suggests our entire cosmos operates in a similar way. The information needed to describe every particle and every force within our volume of space is actually encoded on its outer surface. If this is true, then what we perceive as gravitational waves are not primary phenomena. They are a three-dimensional projection of quantum information processing happening on that distant, two-dimensional boundary. This completely transforms our search for primordial gravitational waves. Their origin is not a quantum fluctuation in a field within our space, but a quantum fluctuation in the underlying code on the boundary. The pattern of those first ripples would therefore be a direct snapshot of the universe's quantum computational state at the moment of its origin. Finding and decoding this pattern would be like accessing the source code of reality. The amplitude, polarization, and spectrum of the primordial gravitational waves would not just tell us about the energy of inflation. They would reveal the fundamental bits and qubits from which space and time themselves are woven. The hunt for these waves then becomes the ultimate scientific endeavor, an attempt to read the cosmic script, the initial lines of code written on the surface of existence that projected forth the entire four-dimensional universe we inhabit. And so we reach our 30th and final theory, a concept that steps back from the intricate machinery of specific models to ask a more fundamental question. What if the existence of a primordial gravitational wave background is not just a prediction of one particular theory, but an inevitable consequence of any viable theory that unites gravity with quantum mechanics? This is the no-theory theory, a profound philosophical stance suggesting that these space-time ripples are a universal signature, a non-negotiable feature of a quantum origin for our cosmos. The logic behind this idea is both powerful and elegant. At its heart, it rests on a principle that has been confirmed in countless experiments, the uncertainty principle of quantum mechanics. This principle tells us that even in a perfect vacuum, at the very smallest scales, there is no such thing as perfect stillness. Empty space is not empty. It is a seething, bubbling foam of quantum fluctuations. Tiny particles and fields constantly pop in and out of existence, a testament to the restless energy intrinsic to reality itself. Now, apply this quantum jitter to the gravitational field. If gravity is indeed a quantum force mediated by gravitons, then the gravitational field itself must be subject to these same quantum fluctuations. At the Planck scale, the fabric of space-time should be writhing with microscopic tremors. Here is the crucial leap. In the standard Big Bang model, without any inflation or other exotic physics, the universe begins in a state of incredible heat and density. In that primordial fireball, these tiny quantum fluctuations in the gravitational field would have been present. As the universe expanded, it would have stretched these fluctuations, potentially amplifying some of them into macroscopic ripples. However, the expansion in the standard model is not rapid or exponential enough to create a significant, detectable signal. This is where the no-theory theory finds its strength. It argues that any viable early universe scenario that successfully produces the large, flat, uniform cosmos we see today, whether it's inflation, a bounce, an emergent universe, or a model we haven't yet conceived, must necessarily involve a period where the universe expands in a way that magnifies these quantum gravitational jitters. The process of taking a microscopic quantum fluctuation and stretching it across the cosmos seems to be a necessary byproduct of creating our observed universe from a quantum beginning. Therefore, detecting the primordial gravitational wave background would accomplish something far greater than just confirming inflation or any other specific model. It would be a direct validation that gravity is quantum mechanical. It would prove that the gravitational field itself is subject to the same quantum rules that govern every other force and particle in nature. This discovery would close one of the most significant chapters in modern physics. For decades, we have had a magnificently successful quantum theory for 3 of the 4 fundamental forces, while gravity, described by Einstein's classical theory of general relativity, has stubbornly resisted incorporation. Finding these waves would be the first direct observational evidence that gravity, too, plays by quantum rules. It would be the smoking gun that physicists have been searching for, showing that gravitons are not just a theoretical convenience, but a physical reality. This elevates the search from a test of cosmological models to a foundational test of our understanding of reality itself. A detection would mean that we have finally heard the quantum whisper of gravity, a sound that has been traveling for 14 billion years. It would tell us that the universe was born from a quantum event and that the fuzzy, probabilistic nature of the quantum world is woven into the very largest structures of the cosmos. Conversely, if after decades of searching with ever more sensitive instruments, we find only silence, a profound absence of these primordial ripples, it would force a radical reconsideration. It might suggest that gravity is, in fact, a purely classical force, even at the most extreme energies, a possibility that would overturn a core expectation of theoretical physics. Or it could mean that our universe had a uniquely smooth and quiet beginning, one that somehow avoided amplifying any quantum gravitational noise, pointing toward an origin story even more strange and serene than we can currently imagine. The hunt for these first ripples is, in this grand view, not just about how our universe began, but about the fundamental laws that allowed it to begin at all. But translating these mind-bending theories into tangible evidence requires a feat of engineering and patience that is almost as staggering as the concepts themselves. We are listening for a whisper that has been traveling for nearly 14 billion years, a signal so faint that it is buried beneath a cacophony of other cosmic and even terrestrial noises. The hunt for this primordial gravitational wave background is a multi-pronged assault on one of nature's best-kept secrets, employing everything from lasers in vacuum tunnels on Earth to the precise timing of dead stars across the galaxy. Each approach listens to a different part of the gravitational wave spectrum, much like tuning a radio to different stations, because the predicted signals from the early universe span an incredible range of frequencies. Let's start with the detectors that first made gravitational wave astronomy a reality. Ground-based laser interferometers like LIGO in the United States, Virgo in Italy, and Kagra in Japan. These monumental instruments work by splitting a laser beam and sending the two halves down perpendicular arms several kilometers long, reflected by mirrors suspended with incredible precision. A passing gravitational wave minutely stretches one arm while squeezing the other, creating a tiny shift in the laser light's interference pattern when the beams recombine. The sensitivity of these detectors is astonishing, capable of measuring changes in distance smaller than 1/10,000th the width of a proton. However, for all their power, they are fundamentally limited in their ability to hear the primordial hum. They are tuned to listen for the high-frequency chirps of cataclysmic events like merging black holes and neutron stars, which oscillate at tens to hundreds of cycles per second. The stochastic background from the Big Bang, by contrast, is predicted to be a low-frequency rumble with waves that might take years or even decades to oscillate just once. These long wavelength ripples are simply too vast for Earth-bound detectors to sense. Their arms are too short, and they are constantly drowned out by lower-frequency seismic noise, like the rumbling of the Earth itself. To access this crucial low-frequency band, we must escape our planet's gravitational murmurs. This is the ambitious goal of the Laser Interferometer Space Antenna, or LISA, a future European Space Agency mission planned for launch in the 2030-50s. Imagine LIGO, but with its arms separated by 2.5 million kilometers, flying in a perfect triangular formation behind Earth as it orbits the Sun. In the pristine quiet of space, free from terrestrial noise, LISA will open the millihertz frequency window, a band where a symphony of cosmic sources is expected to sing. This is precisely the range where many primordial signals are predicted to be strongest, including those from first-order phase transitions, cosmic strings, and the late stages of inflation. LISA won't just be listening for a diffuse hum. It will have the resolution to potentially pick out individual sources within that background, like the distinct chirp from the merger of supermassive black holes at the centers of galaxies. Its data could reveal the detailed spectrum of the primordial background, allowing us to distinguish between the predictions of inflation, ekpyrotic scenarios, and other theories with unprecedented clarity. For the very lowest frequencies, where gravitational waves have wavelengths comparable to the distance between stars, we rely on a completely different and equally ingenious technique: pulsar timing arrays. This method turns the entire galaxy into a detector by using pulsars rapidly spinning neutron stars that beam radio waves toward Earth with the regularity of the most precise cosmic clocks. Collaborations like NanoGrav in North America and the International Pulsar Timing Array combine observations of dozens of these millisecond pulsars. The idea is to monitor the arrival times of their pulses with exquisite accuracy over many years. A passing, very low-frequency gravitational wave will subtly warp the space between us and the pulsars, causing the pulses to arrive minutely early or late in a correlated pattern across the sky. It's like sensing the gentle swell of the ocean by observing how it makes a fleet of buoys bob in a synchronized rhythm. In recent years, these collaborations have announced compelling evidence for a background signal consistent with the combined rumble of merging supermassive black holes throughout the universe. The next, and far more difficult, step is to sift through this noise to find the even fainter, potentially unique signature of primordial waves lurking beneath it, a signal that would have a different pattern across the pulsars than the astrophysical background. Perhaps the most promising near-term hope for a direct detection, however, lies not in listening for the waves directly, but in looking for the permanent scar they left on the universe's very first light. This brings us back to the cosmic microwave background, the afterglow of the Big Bang, as those primordial gravitational waves propagated through the universe for its first 400,000 years. They gently squeezed and stretched the hot plasma, imprinting a very specific pattern of polarization on the CMB light when it was finally released. This pattern, known as primordial B-mode polarization, is a unique, swirling fingerprint that cannot be created by any other known process. Finding it is the holy grail for experiments like the BICEP and Keck arrays located at the South Pole, where the cold, dry air provides an unparalleled view of the cosmos. These telescopes scan the sky, measuring the subtle polarization of the CMB with ever-increasing sensitivity. The challenge is monumental, as the signal is incredibly faint and must be distinguished from polarized light emitted by dust within our own galaxy, a confounding factor that famously led to a premature announcement of a detection in 2014. The next generation of experiments, like the Simons Observatory and its planned successor, the CMB-S4 project, will deploy armies of detectors with vastly improved sensitivity and the ability to map multiple frequencies of light, allowing them to meticulously subtract the galactic foreground and finally reveal the primordial signal if it is there. This method offers a direct snapshot of the universe when it was a mere infant, a fossilized imprint of the gravitational waves that were present at that moment, providing the most direct link we have to the physics of the very first second. Imagine for a moment that the signal arrives, not as a dramatic audio cue, but as a subtle pattern of data, a statistical whisper emerging from years of painstaking observations. This detection would be far more than just another scientific discovery. It would be a key turning a lock that has been sealed for 14 billion years. The immediate impact would be a dramatic narrowing of our cosmic possibilities. The amplitude of the detected waves, a quantity cosmologists call the tensor-to-scalar ratio, is like a cosmic volume knob. It tells us directly about the energy scale of the inflationary period. A loud signal, a high tensor-to-scalar ratio, would mean inflation was a truly violent, high-energy event, happening at energies a trillion times beyond what the Large Hadron Collider can probe. This would immediately rule out dozens of the simpler, lower-energy inflationary models, forcing theorists to focus on a much smaller, more exotic class of theories. Conversely, a very faint signal would suggest a gentler, lower-energy inflation, pushing our explanations in a different direction. In essence, this single measurement would act as a cosmic filter, sifting through a universe of theoretical possibilities and leaving us with a much clearer picture of the forces that shaped our reality. But the amplitude is only the first clue. The true detective work begins when we analyze the shape of the wave spectrum, specifically its tilt. Is it perfectly flat, or does it slope slightly? A flat spectrum, where waves of all wavelengths have roughly the same strength, is a hallmark prediction of the simplest inflationary models. However, a detectable tilt, a slope where the strength of the waves changes with their frequency, would be a treasure trove of information. For instance, many alternatives to standard inflation, like the ekpyrotic universe model we discussed earlier, predict a distinct blue tilt, where the shorter wavelength, higher frequency ripples are stronger. Finding such a signature would be like discovering a specific type of fossil that could only have been created by one kind of prehistoric event. It would allow us to decisively choose between a universe born from a singular inflationary expansion and one born from a cyclical collision of brains in a higher dimensional space. The spectrum's detailed shape could also reveal the intricate dynamics of multi-field inflation, showing us if the universe's birth was guided by a single field or a complex interplay of several, each leaving its unique harmonic signature in the cosmic hum. Beyond refining our cosmological models, a detection would achieve something even more profound. It would provide the first direct, empirical evidence that gravity is a quantum force. For decades, we have operated under the assumption that the graviton, the hypothetical particle carrying the gravitational force, must exist to maintain consistency in our theories. But we've never had any direct proof. Primordial gravitational waves are generated by the amplification of quantum fluctuations in the fabric of spacetime itself. Detecting them would be the smoking gun, demonstrating conclusively that the gravitational field is subject to the same quantum jitters that govern all other particles and forces. This would bridge the last great divide in modern physics, finally bringing gravity into the quantum fold and opening the door to a true theory of everything. We would no longer be theorizing in the abstract. We would be analyzing data from the quantum gravity era, an energy regime so extreme it was previously thought to be forever beyond our observational reach. Ultimately, this discovery would transform cosmology from a historical science, where we piece together clues from the aftermath, into an experimental one, where we can directly test hypotheses about the absolute beginning. It would give us our first tangible data point from the universe's first sliver of a second, a period of time so brief it defies imagination. The implications ripple outward, touching on everything from the nature of the multiverse to the ultimate fate of our cosmos. By tuning our instruments to the faintest vibrations in space, we are not just listening to an echo. We are attempting to read the cosmic Genesis story written in the very first tremors of reality, a story that would, at long last, move from the realm of philosophical speculation into the light of empirical truth. We have journeyed together through a cosmos of ideas, from the explosive dawn of inflation to the serene emergence from a timeless state, from the crackle of cosmic strings to the whispers of a multiverse. We have considered the possibility that black holes were our universe's first inhabitants, that dark matter itself may have roared into existence, and that the fabric of space-time might be a holographic projection from a distant, two-dimensional edge. These 30 theories are not just wild speculation. They are the leading edges of human thought, rigorous attempts to decode the faintest signals from the beginning of everything. Each one represents a different path our cosmic story could have taken, a different answer to the ultimate question of our origins, and the astonishing fact is that for the first time in history, we are building the tools to distinguish between them. This is not merely philosophical pondering. It is a data-driven revolution in the making. The search for these primordial gravitational waves is, therefore, one of the most profound scientific quests ever undertaken. It is a direct assault on the final frontier of knowledge, the absolute beginning. By listening to the echoes of creation, we are attempting to read the first page of the cosmic diary, a page that has been sealed for nearly 14 billion years. A successful detection would do more than just confirm a single theory. It would validate our deepest understanding of physics, proving that gravity itself is a quantum force and giving us a direct window into an energy regime so extreme it redefines the possible. It would tell us whether our universe is a lone bubble, one of countless others in a vast multiverse, or part of an endless cycle of death and rebirth. The implications reach into the very nature of reality, time, and our place within the grand scheme of existence. And the most thrilling part of this entire story is that the next great discovery could be made at any moment. The pulsar timing arrays are already hinting at a cosmic hum. The next generation of CMB telescopes, like the Simons Observatory and CMB S4, are being built with unprecedented sensitivity, poised to scour the ancient light for the swirling signature of inflation. The LISA mission will soon open a new window on the low-frequency universe, listening for the chirps of cosmic strings and the thunder of phase transitions. We are living in the golden age of cosmology, a time when grand ideas are being put to the test. This is not a story that belongs only to scientists in lab coats. It is a human story, a testament to our insatiable curiosity and our relentless drive to understand where we came from. So, stay curious, follow the progress of these incredible experiments, because the whispers from the edge of time are growing louder, and the next voice we hear could be the universe itself, finally telling us the secret of its birth.